Start and need you to stop here.
Okay. Okay. Good. Thank you.
Welcome.
Yeah. Thank you. So, good afternoon, everybody. It's a great pleasure to be here, and thank you for your patience while we were figuring out how to get this going. It's a great pleasure to introduce the speaker today, Marcel Frenken. This talk is part of the OneArchSci series of our European Union funded project with the same name. It's theoretically all about isotopes in archaeological science, how that combines humanities, human remains, how it combines environmental archaeology and material science. And Marcel's talk fits right into that to show the foundation on which these isotopic methods then can build to understand the people of the past, economy of the past, societies, how they organize themselves, how they lived, how they died. So today we will focus on a particularly beautiful material, glass, used almost exclusively for adornment, very little practical use in the prehistorical record, but nevertheless a very technically challenging and innovation-driving material through the last 3,500 years. Today we will focus on a particular time slice roughly 1,000 years ago, where Marcel is studying as part of PhD evidence for the actual making of glass, as opposed to the working, which is much more common. But I think, Marcel, you will certainly tell us more about that yourself.
About working.
So, come on, 45 minutes for you.
Thank you for the introduction. Yeah, thank you for your presence here and your attention also online. Again, sorry for the struggle at the beginning, but now we are ready to start, I think. Let me just insert the timer here so I roughly know when I'm actually supposed to stop. Yeah, so today I will take you to the Silk Roads and the glass production in Akhsiket. First of all, I want to introduce you to a little bit of the literature that is circulating at the moment in this field. I want to highlight some of the problems that we have with it, and that is mainly the current research on early Islamic Central Asian sand ash glass, or as I love to call it, ICAPAC. Well, what to see? Yes. So, continue. Okay. So, as I said, the field is currently dominated by one specific research question, one idea that we're all trying to figure out in relation to glass, and that is tracing the production and tracing how it moved along the Silk Roads. And this idea is reflected again and again in the titles of many publications, so you can always see some kind of provenance. Can you see the pointer? Some kind of production or provenance with the Silk Roads buzzwords, basically. And this happens, as I said, again and again, again and again and again. What is the Silk Roads, and why do we care so much about it? The Silk Roads are a network of trade routes, not necessarily one long trade route, as sometimes we think about, but many connections, many human connections are behind this larger network. It is more of a modern idea than a historical reality, say. Importantly, the Silk Roads are divided into two parts. We have the northern Silk Road and we have the southern Silk Roads. And in the past, a lot of the research attention specifically focused this region that you might know, the Mediterranean and Europe. And in this area, we have, similarly to the southern Silk Road, one predominant method of transport of trade, that is via sea, by ship. Now, moving into Central Asia and into Central Asian glass studies, we are dealing with a completely different terrain. We no longer travel by ship, we travel by land. The dominance of the Silk Road, the cultural significance of the Silk Road is then also reflected not just in the archaeological field, but also in our language today. Maybe you can ask around your friends what their word for tea is or for chai, but it is linguistically a fact that this word for tea has been influenced highly by whether or not the tea was transported via land or via sea. And this difference in thinking and this different mode of transportation, I think we have to incorporate more into our research on the Silk Roads. We need to understand that this environment in Central Asia is wholly and fully different from the Mediterranean Sea, where everything is relatively close by and easily reachable via ship. Because we're not talking about ships, or at least not ships in the nautical sense, but ships in the desert sense. So the Bactrian camel here on the right, left, would be the dominant mode of transportation of goods through the Central Asian mountainous desert landscape. So this issue I have with focusing on provenance as the sole research question for glass is not new. It's been voiced that this focus on provenance is problematic also for other archaeometric disciplines, for example, in metallurgy, where it also often we focus on lead isotopes for provenance, for provenance studies in general. And it is a very compelling idea to know where people connected and how they moved things from A to B. But I would argue that we can lend even more depth to this question by looking also into other things. And by only focusing on this, we are also making some very precarious assumptions. For example, that the most found glass chemical group is the locally produced one, which has led to some pitfalls in the past. As we can see here on this sort of pie chart distribution map, you can see glass compositional groups here. And I want to highlight specifically the S1 and S2 groups, which are now thought to be of Mesopotamian origin, produced likely near or in Samarra. But in the past, we thought that they were from Nishapur, because in Nishapur, we find a vast majority of the glass finds there belong into these two groups. But it seems more and more likely that they were actually imported there from Mesopotamia. And in the cities in between, we still find the Mesopotamian glass, but other groups dominate here. And the assumption now is that these G groups here, except for the G3, are likely local Iranian products. But we don't have any large size. So that is the next issue that I want to highlight, is that we propose a lot of production, a lot of glass production, but we don't actually follow up with any evidence for production. You can see in red the sites where we are proposing that production happened based on glass finds. And in blue, I highlighted those few sites where even the flimsiest bit of evidence exists in the current archaeological record for glass working or production, not even just the primary production. And I'm really talking about the flimsiest bit of evidence. In Herat, for example, I'm talking about documentation, great documentation by Robert Brill from the 1970s, ethnoarchaeological documentation, of course. So he followed a pair of brothers who were still following the glassmaking tradition there, and he documented that in a very fascinating way. But It's not really archaeological evidence. And in the other sites that I'm talking about here, there are publications where glass finds were analyzed. And then in a half sentence, it was mentioned that there is also some furnace material there, or we found some evidence for production or something like that. But there is not really a systematic way to study glass production. So let's look a bit further, a bit deeper into what glass production actually entails. And I want to start with a more simplified version of this flow chart that I came up with. Glass is made from two components. One is the silica and the other is a flux to reduce the melting point of the silica, because otherwise you need to reach really high temperatures, and it's not a feasible way to produce or work glass. So this silica source can be two different things. It can be either a sediment or it can be a rock. So a coarse grained rock. And the flux in the Mediterranean, we know a lot of natron glass and mineral flux, but then later and earlier, we also know plant ash. So ash made from halophytic plants that grow on saline soils that take up the soda or the potash from the ground. And when they are ash, we can use this as a chemical component for glass or for soap. So, and glass, at least in theory, is an object that can be infinitely recycled. As long as we don't mix it too much with different colors, then eventually we end up with black glass, not very desirable, except for certain use cases like bangles or beads. But we will see where the recycling is a topic that is still researched, but it is highly complicated to figure out. So now let's look at a bit deeper into that. So as I already mentioned, we can have different kinds of raw materials. And the provenance assumption fundamentally relies on the consistency between the geochemical signature of the raw materials and the end product, because the end product is what we are analyzing. And if there's anything in between that changes this fingerprint, we have to know about it. Otherwise, the provenance that we are coming up with might be flawed, or at least our reasoning might be flawed. So the chain of repertoire of glass, as I said, can very complicated. We start with the primary production. We take raw materials, we melt them, and we end up with glass. We could then immediately start working the glass into an object, or we could export raw glass in the form of ingots or just chunks to be remelted in a different place and shaped into objects there. Then after an object has been finished, we could recycle it and go through this whole process again, or we could end up in the archaeological record where we can actually sell it. And along this chain of repertoire, you can see I highlight multiple opportunities where chemical alteration to the geochemical signature of the raw materials could happen that we need to study. And I highlighted also multiple opportunities for where trade actually could happen. And I think this is another important factor that is often overlooked, that just because we know a product is imported, we don't actually know at which stage of its life cycle it was imported. Are we talking about raw material import? Are we talking about finished object import, or anything in between? And figuring this out, the chain of repertoire, and where things actually happen, and what might be altering our results without us knowing about it, I think is an important new addition to this research field that we need to put more attention towards. And with this 10-minute rant now, I want to finally start looking into Akhsiket. As I said already, the Central Asian side, the Fergana Valley of Uzbekistan, right here in between this cursor, in between the Tian Shan Mountains and forming a sort of oasis on the way into northern China. So it is a very important hub in the northern Silk Roads because of its geographic location. So the fact that it's a bed with water. So the site now, we have an outer walled city and an inner citadel. And on the drawing, you can see that our proposed glass workshop, where we actually found some furnace material, is located here in the inner city or on the wall of our city, object 24. I will also later mention things or finds from object 9 here in the corner and object 23 outside of the wall. It's a stratified dumping area where all kinds of waste from the city was expelled over the wall. So in this object 24, the proposed workshop, we find furnace material. It's some kind of organically tempered clay. We can still see imprints of plants. And we can see rubification, so was exposed to heat. And we also find drippings and clippings that signal, at the very least, glass working. So these glass furnaces, they were usually dome-shaped, sometimes circular, sometimes also rectangular, other shapes, because they need to reach very, very high temperatures. So you need to have a good circulation within, you need a chimney, lots of fuel, and you need an opening to access the glass if you want to work it. And then there's various methods. Both of these pictures depict glass blowing, but there you can also mold it, or you can do different things with it. And what we have are just pieces of a furnace. We don't really know what the shape of the furnace is or what the size of the furnace would have been. But what we can say is that it was likely a two-layered construction. We have bricks and we have an inner organic tempered insulating layer that was plastered on top of bricks, or maybe used as a reinforcement of some kind. And looking into this material, we do what we do and we take samples of it. We can still see the brick structure with the attached plaster onto it, and then where the glass starts melting to both the brick and the organic tempered insulating layer. And those are the two areas that I really want to highlight that I will discuss further now. Is A, where the brick starts melting into the glass. See you close up here, the corner of the brick and the glass. And the other area is here, where the brick and the organically tempered clay adjoin. So first, I'm going to show you a picture of the partially molten brick and what that looks like, in order that we can later understand the actual production evidence that I'm going to present. Still holding out there. What we see here are olastenite crystals, so a calcium silicate that has recrystallized from the melting ceramic. You see a lot of porosity from gases, carbonates going there that cause bubbles. And we see some what are called Schlieren. It's a German word that just means like stripes, or we can see mixing of two different glass compositions into each other, frozen in time and space. So what we see here is a rich in silica melt and then a slightly silica poorer ceramic. And the exactly opposite way it is for alumina and calcium. So we see calcium-rich ceramic, relatively calcium-poor glass, and alumina-rich ceramic melting into and slowly mixing into the glass. See the glass melt a little bit darker in contrast here, and the alumina really lighting up in the ceramic, or in the former ceramic in the melting brick. And then I want to point out, just for understanding, that the organic tempered fabric that is plastering the bricks, you can see here the joint that I was talking about earlier. is chemically almost the same as the brick material. So we could argue that it melting into the glass would look exactly the same. There's a little bit more porosity there, so the organic temper, but chemically they are nearly identical. And now, the highlight of the Akhsiket finds: ceramic with white material attached to it. This is what we initially thought might relate to glass production, or to primary glass production, I should say. And we can see it is present in different stages. We have one porous white material only with a very, very thin slice of glass. You cannot see it in this picture, but it is there, it is up here. And we can see one that is progressed much further, where there is a discernible glass, green glass, with still some of this white material on top. So what is this, and why do we think it's primary production? It is coarser grained than it has grains, so it is not a glass, it's not a fully formed glass. And what this could be is frit. Frit is an intermediate product. It was only a little side note on the flowchart that I showed earlier for the primary production, because it's not a necessary step in the production, but it is an optional one. So when you don't reach high enough temperatures to melt all of your silica, what is going to happen is you will form quartz grains, residual quartz grains, with an interstitial glass forming between them. But eventually you will reach a solubility limit for the silica and it stops dissolving, or you stop the process by stopping to heat it, and you are left with a not fully formed intermediate rod. Not saying necessarily this was intentionally done, this might be on accident, but we do have evidence from Bronze Age Egypt that it was also intentionally done, and it is essentially similar to faience in its composition or in its structure. And this is exactly what we see in this material. We see coarse quartz grains with a highly weathered glass in between. What is left over of this glass, and it's really very badly corroded. And if I show you now the element distribution maps of silica, we see a similar picture to what we saw earlier, but we see high silica melt here with coarse grains in it, and then the alumina forms a very nice border here. We have a lower alumina in the top where the glass melt is supposed to be, but we still have these large grains of silica there. So it's not really a glass, it is something in between. And this is essentially residual bench material. So we have evidence here for primary production, because we have raw materials in situ found attached to furnished material. So they were really melting raw materials here, not re-melting pre-existing glass. It's not one. And this now is an image of the slightly further progressed area, the same frit material. We still have very few residual grains, and otherwise pretty much the same story, just very few residual quartz grains. You can see one right here on the border with the ceramic, and you can see also the grain size difference very good here. That the grains that are in the raw material batch are much, much larger than you find in ceramic. Compositionally, it is on the way to glass, but there are some important differences. For Central Asian glass, the alumina is quite low, except for this sample Akhsiket 24-3, which above 3%, up to 6% sometimes, is normal for Central Asian glasses. But we find lower alumina here in the frit. Curiously, we do find some evidence for decolorants or colorants in the glass, and for comparison here you have a chunk of glass, fully formed glass, that also shows here the slightly higher alumina, and also a slightly higher potash in the fully formed glass, which explains maybe also why we are dealing with not fully formed glass, because the composition wasn't quite right, or maybe we are just in a cold corner of the furnace where it didn't quite reach high enough temperatures. That we can also conclude from the phase diagram, where we see that the red dots sit in a slightly lower melting corner of the ternary, whereas the fully formed glass sits up here, where you need higher temperatures to fully melt it. Further evidence, therefore, maybe the composition wasn't quite right. I'm not saying that the frit was intentionally produced. I think they were very capable of reaching high enough temperatures to complete the full glassmaking process. It's one step, but we do have evidence. We do have the frit, so we can say that we have the production here. That being said, I mentioned earlier already, ability can happen at different states. So we have primary production here, but that doesn't mean that glass wasn't important. I mentioned earlier the site or context 9 near the outer wall of the cities, and this is where we found glass ingot. It's cobalt blue glass ingot. This one is likely imported. There's no evidence for cobalt blue glass making, and these vessels are quite rare in the Akhsiket context to begin with. So it's unlikely that the glass was produced locally, but maybe it was formed to match the local tastes and shape and requirements, or maybe just because the ingots were easier to transport. But we do have evidence for both primary production and import of glass. So we can conclude that frit provides evidence and therefore precedence also for further research into production of glass and how we can go about dealing with the production remains that clearly are there, that are mentioned in the publications, but they are not really studied. And I think now we have shown that there is something we can learn from this material, even if it is just waste product, essentially. And as I said already, the intentionality of the intermediate product, frit, I don't think is given here because we only have very few samples of that. We don't find a lot of it. So it's more likely that it was accidentally made or not intentionally made. And the chemical difference between the vitrified and loaded ceramics and the frit material can be seen in the silica, in the alumina content, and also by the grain sizes of the remaining quartz grains that we have. And now I want to go back to the second part of my presentation, showing you this flowchart again, because there are, so for now we have dealt with the frit and with showing how primary production can be established in a site. Now I want to look at this bit, at the chemical alteration of the raw material signature that might be relevant for provenance. And if you look at you can watch the glass document, Glass Makers of Herat by Robert Will. I highly recommend it. And in there you can see the two brothers crushing quartz pebbles that are about a little bit smaller than a fist, quite smaller than a fist, but larger than sand, into a powder to make their glass with in a grinding tool. Grinding tools are made from rocks, silica-rich rocks, also, or from metals in later stages. So what we did was we got some quartz pebbles and we crushed them into sand, essentially, to see if the type of grinding tool, the rock type or the metal type, would have any effect on the chemical composition. And to do that, we first processed the quartz pebbles into two different grain sizes. So ignore the above 300 one. I just showed this to highlight this fragment of brass that is actually still visible here in the photograph also. But the glass was made with less than 300, so we just used a sieve to achieve that. And then the flour is what we used a sort of finger test to do that. When the flour sticks in between the grooves of your fingerprints, then it's ready to be made into glass. It's fine enough. Would be more towards silt and sand, essentially. So here I'm showing the composition of the rocks of the grinding tools. And I want to highlight specifically the low iron in the granite compared to the other two rocks. Compared to the quartz is so high, but quartz it's relatively pure material here. As you can see, it's almost 100% silica done with WEXF. And I want to highlight the high chromium in the basaltic andesite volcanic rock. And then the high lanthanum in the granite, more acidic, different kind of plutonium. So we went on, we mixed the quartz powders that contain the potential contamination with our fluxes, in our case, soda and some lime. And then we fired them for 3 hours at 12 degrees to achieve a nice glass melt. And this is what came out. So one thing that all of you can immediately see is that the colors are quite different. The blue, perhaps unsurprisingly, comes from the copper and the brass. So both of the cases where we used either a full brass mortar and brass pestle set, or for the second, for the basaltic andesite, we used a basaltic andesite mortar, a base, and the brass pestle. But even just pestle was enough to give this deep blue aqua color. Not blue, copper. Okay, iron aqua. This one is maybe a bit of a mix of aqua and blue. And then the other thing I want to highlight is, despite the low content of iron in the granite, we do see more greenish color here than in the basalt, which had much higher iron. How is that? So it seems that, and we can also analytically determine that, different elements are, depending on the rock type, transported into the glass in different ratios. So it's even more complicated than we thought to begin with. It's not just dependent on the rock, but also on the structure of the rock. It's not enough to have just a bulk composition of the rock. You also find about which minerals are in the rock, and which ones are softer and which ones are harder. So in the quartz, or in the granite, we have a lot of quartz, which maybe preferentially stays in the granite, whereas the mica that contains some iron is then soft. It moves into the glass batch. Okay, I was meant to highlight this as I was talking about it, but I forgot to do that. So let's move through that. So analytically, I said already, we can show that there is a contribution from the rocks. We're still producing more data, and very importantly, we are working on a blank, which was crushed quartz and then further crushed into in an agate mortar. Thank you. In order to keep the contamination to minimum or non-existent, because the agate is also 99.9% silica. So there shouldn't be any contamination there, and we don't have the results of those samples yet. But what we can show is that we have a clear mixing line between the rock and the glass that we are melting. And to compare this to archaeological glass, to see actually on a scale that is relevant to archaeological glasses, we put some in there. Or Jinjin did this. Thank you. I think he's in the audience. And we do see that overall the trace elements in lanthanum are generally quite low. We are talking about tens of ppm here. And in the granite one specifically, we have a lot of contribution in lanthanum. And in chromium, same story. In a rock that has a high chromium, and here that's for the basaltic andesite, which had the rock at over 900 ppm of chromium. And now in the glass, we still find roughly 10 to 20 of those 900 still. And this is on an order that is relevant for interpretation. If we mix a silica source that already has some or not with this grinding method, then we do change the geochemical signature of the raw materials. We need to take this into account when we are looking at provenance. And with that, I also want to conclude that grinding tools can have an effect on the composition, and we need to take it into account. But currently, we have no idea how to prove that grinding tools were used in glass production. We don't know if they used a rock and crushed it down, or if they used a sediment that was rich in silica. You have to find a very specific sediment, because if it contains too much iron or too much other stuff, you will end up with a very ugly glass or with no glass at all. So either way, it shows that they're refining their techniques in a way that suits their environment and that suits their resources that they have. But we still need to figure out a good way to know grinding tools were used. And this contamination could contribute to knowing that by showing that locally available rocks would mix into this into the glass composition. But this is something that we have to invest further research into. And with that, I want to thank, first of all, the original excavators funded by the Royal Society, the Gerda Henkel Stiftung, and then especially Dr. Narbaev and Dr. Maxudov, and also Anna Azorio for doing some initial work on Akhsiket and providing valuable archaeological guidance. And then I want to thank also Dr. Chin Liu for doing isotopic and trace element analysis on the samples that we are still working on, continuing on. And also, of course, my local colleagues and the Ventures Foundation for funding my position here, and then the OneArchSci science project for allowing some search visits and training Leuven, where we also did some learned how to do trace element analysis. Yeah, with that, thank you for your attention. Very good. Are there any questions? Online or locally?
Online.
Online, no? Ah, okay, sorry, no online questions.
Can you access the online questions?
Not yet.
None.
No.
Okay. Good.
Yeah, I can see boom, and I can see the chat, so I don't know if people can write chat.
Stella asked if I've just joined online.
I mean, I can see the chat, I just don't know if people can actually write it. I don't see anything like that. Okay.
Good. So, do we have any questions? Andreas.
Thank you, Marcel. It was really impressive, especially the second part where the colors. I want to ask about the nice blue color. So, how much of this, let's say, have you estimate the quantity of the brass or copper? Yes, in order to provide this very nice.
In the glass is less than
1%. Okay, so it's enough to provide them. Yes,
more than enough.
More than enough.
This very deep blue color, probably more copper than would be added in archaeological samples. I don't know if it's more than 5%.
But it's a continuum, it then goes to the red glasses.
Yeah.
But you can have around 1%. It starts with roughly 0.5% that you start seeing it. You have the analytical data for these, so
We do.
yeah.
In your conclusions, you said studies in archaeological grinding tools are rare. Even though they are rare, the ones that are available, did you interrogate them? Did you try to?
We try, but the problem with those that are there are a lot of the times they're just typologically. So they focus on the shape, the potential use of the grinding tools. There are many out there that do what is it called? The scratches, the micro wear, macro, yeah. This type of analysis, wear analysis, yes, thank you. But very rarely do we have, well, I don't know of any that focuses on compositional analysis of those grinding tools, or would study how they interact with rocks, because rocks is not, when you find grinding tools, most likely you will associate them with grain or with cooking, making flour, but not with glassmaking.
Obviously, when those people are making their whatever, they don't have intention of that archaeologists will study them later. So, so it's not.
That is one of the problems we have, that might find grinding tools associated with glass workshops, but then the grinding tools are not associated with the glass workshop because they don't show any glass on them, so they're interpreted in other ways.
You would need to see quartz on the value. Quartz is such a common environmental mineral.
Yeah.
It's non-diagnostic. So making that point that these particular grinding tools are glass related is theoretically probably unlikely.
Yeah, maybe the use where could.
People are trying it with grinding ore
Okay.
in copper smelting and trying to see are there any traces left. And even that is very difficult, and I'm not sure how many successful cases have been done.
And in metals, there is also a fundamental difference there, because in metals you have a purifying process coming from the ore, whereas in glass you have an additive process. Like everything that you melt with the glass will stay in there somehow, either as a colorant or as some kind of contamination, but it won't just, you're not trying to get it out anymore once it's in there. You're just melting everything together. So these traces of grinding tools are perhaps more relevant there than for metals. The silica, for example, in the metal would just go into the slag and disappear, but in the glass, it stays in there.
Good. Oh, yes.
I will continue with the blue, the nice blue. Are there any sulfur inside the composition of the? Yes. Combined with copper?
No. When the copper comes in this case from brass mortar, so yeah, and sulfur would likely burn off for the most part. There might be some, in archaeological cases, there might be some sulfur coming from plant ashes. Some more stable components there, but
the archaeological glasses have to be around 1/3% sulfur trioxide. So maybe 0.1% sulfur. But here I wouldn't expect it because it comes from the metal and not from proper plant ash, which has sulfate.
and we didn't use plant ash, we used chemical component.
Well, there is a case where that sulfur affects the color. When you have iron, typically as a contaminant, if you have strongly reducing conditions, you get this nice amber color from the iron sulfur complex. But you are operating in an electric kiln, pretty oxidizing.
Yeah. So we could not use that, but the amber colored glasses are present.
Yeah.
Archaeologically, yes. In a lab, no.
Okay, thank you.
Can't have wood-fired furnaces. Struggle already firing wood in our furnaces. Good. Anything else?
Color.
Any color as long as it's blue. Good. Then let me thank you again, Marcel, for the nice talk.
Thank you for the
And best of luck for your final stretch in your PhD.
Yeah.
And you tie it all together.
Maybe I'll
nice
drop
note.
by again towards the end.
Before your PhD, you will want to see me? Oh, yeah. Good.
Okay.
Can stop recording.
I can stop recording, yes. And thank you also again to the online audience. We're leaving you into the afternoon now. Sorry.